Welcome to Godsmacked, where AI collides with ontology and your old self doesn't make it out alive. Not safe, not scripted, not sorry. This is for founders, thinkers, and creators who crave more than conversation. They want confrontation. We don't talk about change, we engineer it. No fluff, no filter, just tools, truth, and transformation. Welcome to your initiation.
Welcome back to the Deep Dive. Today, we are really opening the hood on something pretty fundamental. It's the infrastructure that's making AI agents smarter, faster, and, this is key, way cheaper to run.
Yeah, it's a big shift.
It really is. So if you're watching how AI is moving beyond just, basic tool use towards genuinely autonomous workflows, well, this architectural change we're talking about, that's the engine driving it.
Absolutely.
Our mission today, then, is to really get our heads around one crucial change. This shift from basic AI tool calls to much more sophisticated code execution. And we'll look at that through the lens of something called the Model Context Protocol, or MCP.
Okay, so MCP. Let's keep the definition really simple to start. When it launched back in November 2024, MCP basically solved this massive fragmentation problem we had.
Right.
Before MCP, if you wanted an agent to talk to, say, Google Drive and Salesforce, you needed totally custom, separate integrations for each one. It was a nightmare.
Yeah, bespoke connections everywhere.
Exactly. So MCP fixed that. It created an open standard. Think of it like a universal language, a protocol. Developers just implement MCP once on their tool or data source.
Wow.
And suddenly, any agent that speaks MCP can access this whole ecosystem. Thousands of tools, data sources, didn't matter who built them. It pretty much became the standard overnight.
And that universality, that success, is kind of where the next problem starts, isn't it?
That's it, precisely.
MCP gave agents these incredible superpowers, connecting them to maybe hundreds, even thousands of tools across dozens of servers. But then they immediately start, collapsing under the weight of all that potential knowledge.
Yeah, they got bogged down.
Okay, let's unpack that scaling failure. What went wrong?
Exactly. We immediately ran into what people started calling context overload and token bloat. When you give an agent access to basically every single API in your company,
You just overwhelm it.
you overwhelm its short-term memory. Yeah.
And for everyone listening, when we talk about the context window, just think of it as the agent's workspace or its short-term memory.
That's a good way to put it.
It's that limited space where the model processes the request, the instructions, and any data it needs right then to do the job.
And if that workspace gets too full, too cluttered, the model slows right down, gets super expensive to run, and maybe worst of all, it starts making mistakes.
Okay.
And with that original method, the direct tool calling method through MCP, the context window was getting hammered in two main ways.
Right. What's the first one?
First up is tool definitions overload. See, most client systems, the way they were built, they load all the available tool definitions right at the start.
All of them, even if the agent only needs one.
Yep. So if your agent is connected to, 1,000 tools, it has to process these detailed definitions, the names, the parameters, the schemas for every single one, like gdrive.getDocument or salesforce.updateRecord. We're talking hundreds of thousands of tokens sometimes, just definitions, before it even starts reading what you actually asked it to do.
That's like forcing the agent to read the entire library's card catalog before letting it find one specific book. Huge upfront cost.
Massive friction, yeah.
Okay, so that's definition overload. What's the second, you call it more insidious problem?
The second one is how intermediate results consume tokens. So when the model makes one of those direct tool calls, the entire result from that tool has to flow back into the model's context window.
The whole thing.
The whole thing. Let's use that concrete example from the source material. It makes it clearer. You ask the agent, okay, download my meeting transcript from Google Drive and attach it to the relevant Salesforce lead. Pretty standard task.
Okay, sounds simple enough.
So step one, the agent calls the Google Drive tool. Let's say it's a 2-hour sales meeting transcript. That could easily be, 50,000 tokens long?
Right, a big chunk of text.
That full 50,000 tokens floods right into the context window as the result of that first tool call.
Got it. So it's sitting there in the agent's memory.
Exactly. And then when the agent figures out, okay, now I need to update the Salesforce record, the model has to essentially copy and paste that entire 50,000 token transcript again, this time writing it into the data field for the Salesforce tool call.
Whoa. So the whole transcript goes through the model's context twice.
Twice. For just one simple task.
That just seems incredibly redundant, and that's what slows everything down and makes it so expensive, right?
That's the killer. It's expensive in tokens, absolutely, but also think about the complexity. The model now has this tricky job of perfectly copying these huge documents or complex data structures from one place to another.
Yeah, the chance of error must go way up.
It does. So if that old architecture is clearly hitting a wall, I mean, it sounds like we needed a totally different approach.
Definitely. But replacing it with agent-generated code, that sounds kind of risky, doesn't it? Doesn't that bring in huge security issues, latency problems? What if the model just hallucinates some bad code?
And that's the core tension, you're right. It's that inherent risk versus this massive potential efficiency gain. But the solution, and this is interesting, it borrows heavily from decades of software engineering history. It's code execution.
Okay.
So instead of calling these predefined tools directly, MCP servers are now presented more like code APIs. The agent actually writes code, usually something like TypeScript, to interact with them. And crucially, it does this inside a secure, sandboxed environment.
Ah, okay. So it's not just running wild.
No, definitely not.
This is where those structural problems we talked about, the definition overload, the result bloat, this is where they get solved. But using patterns we already know from software.
Exactly. It's elegant, really. Let's look at the definitions problem first.
How does code execution fix that?
Well, by presenting the tools like files in a file structure, just like navigating folders on your computer, we completely remove the need to load everything up front.
Oh, I see.
The agent can just explore the file tree. Maybe it lists the .servers directory to see what's available. Then it only loads the specific definition file it actually needs for the task at hand, like getDocument.ts.
So definitions get loaded on demand just in time.
Precisely. Saves a massive amount of that initial context load.
Okay, that makes sense. And what about the results problem? The transcript going through twice.
That's the other big win. Since the agent is executing code in this secure environment outside the model's main context window,
Right.
it can pull that massive data set, like the transcript, process it, filter it, transform it, whatever it needs to do, right there in the execution sandbox.
Before it goes back to the model.
Yes. Only the highly condensed final result, maybe a summary, or just the 5 most relevant lines from a spreadsheet only that gets passed back into the model's context for review or the next step.
Okay, wow. So the model never even sees the full raw data in many cases.
Exactly. And this is where we see that truly stunning efficiency number that gets quoted. That typical process we walked through, pull a big doc, push it somewhere else using code execution, can cut token usage from, say, 150,000 tokens all the way down to maybe 2,000.
Hold on. From 150,000 down to 2,000, that's,
Yeah.
what is that? A 98.7% reduction.
Yeah, around that mark.
That's not just optimization. That's a complete game changer. It feels like it fundamentally restructures the whole economy of running these agents. It slashes costs and speeds things up almost entirely.
It really does. It makes certain tasks that were just too expensive or too slow before, suddenly perfectly viable. And like you touched on, the benefits go way beyond just saving token costs. This code-based approach gives the agent much, much better control.
How so?
Well, think about progressive disclosure. We mentioned the agent can load definitions on demand by looking through files. That's one way. Or if it needs finer control, maybe there's a special search tools utility. The agent can use that to ask for exactly the level of detail it needs about the tools. Maybe just the names first, or names and descriptions, or only as necessary, the full schema.
So it tailors its own memory load based on the task. Smart.
Very smart. It conserves context.
And then there's the really practical benefit you mentioned. Context-efficient tool results. Filtering the data before it hits the model's memory.
Exactly. Let's take that spreadsheet example. Say you fetch one with 10,000 rows.
Okay.
With the old direct call method, boom, 10,000 rows flood your context window. The model has to wade through all that.
Right.
Now, the agent writes a little snippet of TypeScript in the sandbox, something like, filter this sheet for rows where the status column equals pending. Maybe only 5 rows match.
Ah.
So the agent just sends those 5 relevant rows back to the model for review. Instead of drowning in 10,000 lines of mostly noise, the model sees 5 lines of clear, actionable signal.
That has to massively reduce the model's cognitive load
Right.
and make it less likely to miss the important stuff.
Absolutely. And another thing this enables is something human programmers use constantly, more powerful control flow.
Meaning?
Meaning the agent can use familiar programming tools like loops, if conditions, error handling, all within a single step of code execution.
Okay, give me an example.
Sure. Say you need the agent to wait for a specific notification to appear in Slack, maybe confirming a deployment finished.
Okay.
With the old method, the model would have to call the Slack tool, check the result, no notification, wait. Call the tool again, check the result. It's this slow back and forth loop involving the main model every time.
Yeah, very iterative and potentially slow.
Very. But with code execution, the agent just writes a simple while loop with maybe a timeout condition. That loop runs entirely within the secure execution environment, constantly checking Slack until the notification appears or the timeout hits. Then it reports back once.
Much faster. One step instead of many model turns.
Dramatically faster, yeah.
Okay, this is all making agents more efficient, more capable.
Yeah.
But let's pivot to something critical for you listening, especially if you're in an enterprise setting.
Yeah.
Privacy.
Yes, this is huge.
Because these intermediate results are processed and filtered in that separate, secure execution environment, data that you absolutely do not want the main language model to ever see. It never enters its context window.
It stays contained.
And the source material has this fantastic example, PII tokenization. Let's say an agent needs to process a spreadsheet, and it's full of customer contact info, emails, phone numbers, names, stuff you really don't want the LLM potentially learning or leaking.
Right, sensitive data, PII.
So with this code execution setup, the MCP client, the part running the code, can actually intercept that sensitive data as it comes out of the spreadsheet. You can tokenize it, turn the actual email jane.do@example.com into a placeholder like email1, turn the phone number into FIFONE1, the name into NameELE1 before any of that data ever reaches the agent's main context window.
That is a massive security and privacy upgrade. The model itself only ever sees these anonymized placeholders.
So it can reason about the structure of the data. Like, okay, I need to put email1 into the email field in Salesforce, but it never sees the actual sensitive value.
Exactly. And that PII, that real email address, only gets untokenized at the very last moment when it's being passed directly into another trusted tool, like that Salesforce update call.
So the sensitive data flows almost directly from the trusted source system to the trusted destination system, effectively bypassing the language model's memory altogether.
Yep. This ability to kind of firewall sensitive data, it's absolutely indispensable for enterprise adoption. People need this level of trust.
Couldn't agree more. Now, there's one more piece to this code environment puzzle: state persistence and skills.
Right, because the agent now has access to basically a little working file system within that secure execution environment.
Like Scratchpad.
Kind of, yeah. It can actually write intermediate results to files. So maybe it queries a database and gets 1,000 relevant sales leads. It can just save those to a file like .workspaceleads.csv.
What does that enable?
Well, it means the agent can track its progress on longer tasks, manage complex multi-step projects, and crucially, it can even pause and resume work later without losing all its intermediate findings. The state is saved to the file system.
That's huge for longer running tasks. And this idea links directly to skills, right?
It does. Agents can actually start to persist reusable pieces of code they figure out or are given. Maybe it develops a really efficient function for, I don't know, like say if she SSV, it can save that function code in a special skills folder. Sometimes people even have them add a little documentation file like a skill.md explaining how to use it.
So the agent is effectively building up its own personal library, a toolkit of reusable expertise.
Exactly. It makes the agent better and better at specialized, complex tasks over time. It learns and retains capabilities.
Okay, so we've laid out some massive benefits here. Huge efficiency gains, way better security and privacy, this ability for agents to effectively learn by saving state and skills. It sounds almost too good to be true. So what does this really mean for people actually building these systems? There must be a catch.
And that's the necessary caveat. You're right. Code execution gives you all these transformational benefits, but it absolutely adds operational overhead. There's a trade-off.
Okay.
Running code generated on the fly by an AI. That requires a pretty sophisticated and, above all, secure execution environment.
Right. You can't just let it run anywhere.
Definitely not. You need robust sandboxing to isolate the code, strict limits on resources like CPU and memory, good monitoring, debugging tools. It's significant infrastructure.
Infrastructure that those simple direct API tool calls completely avoided.
Exactly. So developers and platform teams now have to weigh that implementation cost, that operational complexity, against the undeniable performance cost and capability benefits.
Absolutely. It's a classic engineering trade-off.
Yeah.
So maybe the core insight here, wrapping things up, is that many of these really complex, kind of novel problems that agents are facing today, managing context, persisting state, filtering huge amounts of data efficiently, the solutions are actually coming from applying these familiar, well-established patterns from software engineering.
That's a great way to put it.
The agent is, in a way, learning to become a pragmatic, efficient coder itself using the tools humans developed.
It's really an incredible convergence to watch, isn't it? We're seeing these AI agents rapidly adopt concepts like file system navigation, reusable functions, structured error handling, robust control flow, things developers have relied on for decades to build complex, reliable software.
Yeah.
So the provocative thought I'd want to leave you with today is this. If AI agents are already so quickly adopting these fundamental software engineering concepts, file systems, reusable skills, essentially becoming coders, what are the next big software paradigms they're going to incorporate?
Ooh, interesting.
Think about things like, I don't know, version control, or maybe principles of modular design like microservices. What established engineering practices will they adopt next to achieve that next leap forward in their efficiency, their reliability, and their safety?
That is definitely something crucial for you to chew on, especially if you think about designing or deploying your next generation of these increasingly capable connected AI workers.
You've been godsmacked, but listening is the easy part. Now it's time to build. Join us in the Forge, where the episode becomes action and clarity gets weaponized. First initiation's on us. Access is limited. Courage is required.